What is our universe made of? It's the biggest unanswered question in science.
Despite the name, space is not an empty space at all.
Space itself is something.
There's a hidden structure and a force that exists within space itself.
Space is very much a dynamic, incredibly active medium.
A force that connects everything in our universe.
It's an active player in the game of life.
It underpins our reality, tying together all of space and time since the very beginning. We call it space-time.
It's everything. Space-time is what the universe really is.
Space-time is how our universe works. But what exactly is it? And how does it control our past, present, and future? We can't see it. We can't touch it. But without space-time, we wouldn't be here.
Space-time is the fabric of our reality. It shapes and governs our lives.
If we want to understand the story of the universe, it's absolutely crucial we understand how space-time behaves.
Space-time has been active since the beginning of everything and is the key to the evolution of everything.
We have to understand space-time in order to understand the history of the universe, to understand how the universe began, how it evolved, and what's going to happen in the future.
The story of space-time is the story of our universe. To know how the story plays out, how it will end, we need to go back to the very beginning. To a time when there was nothing. No stars, no space. A time before there was time. Then, all of a sudden,
our entire universe was born in the Big Bang.
It started in an instantaneous moment where, from nothing, our universe was created.
The very definition of the moment of the Big Bang is that space and time were created at that instant.
It is, as far as we currently know, the coming into existence of space and time itself.
The infant universe, a tiny speck of energy and space-time, materializes from nowhere. Then, the universe suddenly expands.
The idea of inflation is that a very tiny region in an incredibly short amount of time, far shorter than a second, grew by many, many, many orders of magnitude. So imagine myself suddenly becoming the size of a galaxy.
In a fraction of a second, the universe grew from smaller than the size of an atom to the size of a baseball. In cosmic terms, that's like a grain of sand, growing almost to the size of the observable universe.
The universe, at the instant of inflation, actually expanded faster than the speed of light. It seems to be a violation of everything you've heard in physics.
You may be thinking, hey, Mr. Astronomy Guy, nothing can move faster than the speed of light. And it turns out that's kind of true.
But the rule is, nothing can move through the universe faster than the speed of light. In inflation, it's space itself that is expanding. So there is no violation, there is no paradox.
Inflating fast, the universe went through a phenomenal growth spurt.
At the moment of the Big Bang, space-time was this entity that was flying out in all directions. It was space itself that was expanding.
But the universe didn't expand evenly.
One spot in the universe was ever so slightly more dense than a spot right next to it. And we're talking about a tiny, tiny fraction of a percent. 1 part in 100,000. But that was enough.
Fluctuations in expanding space-time created areas with higher density. Inflation made these high-density regions larger. And this allowed our universe to take shape.
When parts of the universe didn't inflate quite the same way as others, all of a sudden things could start to come together.
As the universe cooled, energy turned into matter. And in the denser regions, that matter started to clump together. Crucially, these regions had more mass than others.
Mass bends space-time, so anything that is made of matter bends space-time, and the more matter you have in one place, the more you bend it.
In fact, I'm bending space-time right now. When I flex, I bend it even more because of my incredibly high muscle density. I don't bend at the maximum. I don't want to destroy the Earth and the solar system, but you know, it's an effect. It's a real thing.
If I had imaginary glasses that allowed me to perceive directly space-time, suddenly those hidden aspects of a curved universe are as visible as the hand in front of my face.
We'd see a curving grid of space-time moving and reacting to objects within it. And we'd feel the curving of space-time as the force we call gravity.
Gravity is different from all the other forces. It is intimately connected with the curvature of space-time.
Something that can bend space and time has gravity. That's what gravity is, the bending of space and time itself.
It's hard to visualize this, but a good analogy is a trapeze artist and their safety net.
You can imagine a trapeze artist falling into a net on purpose. That net is flat and looks like a nice, orderly, evenly spaced grid. But when they fall into it, they distort that grid. Well, that's a lot like space. If you have matter in space, it warps the framework. When the trapeze artist is resting in the net, they're bending that space-time grid a little bit. If you had two trapeze artists in there, double the mass in roughly the same volume, you would get a bigger dip. You have a bigger distortion. And that's how space-time works.
More mass equals a bigger curve in space-time equals more gravity. But understanding the nature of gravity and space-time is no easy thing. It's an idea developed by one of the greatest minds ever.
Einstein had the idea that space itself is something that can be bent, something that can be stretched, that we are all bound together by space-time.
Einstein says that space and time have a geometry. They have a life of their own. They have dynamics.
Those dynamics are what we call gravity. The more dense the region of matter, the greater the gravity, the deeper the curve. This connection is the foundation of our physical reality.
It's the interaction between matter and energy and space-time that created the universe that we see around us today.
But that doesn't mean we fully understand it.
There's much more that we don't know, and that's frustrating. With the laws of physics, I can talk about how space-time behaves, but it does appear to be something that stretches, that contracts, and that gravity is the embodiment of space-time.
Born in the Big Bang, space, time, and energy combined to create our infant universe. These basic materials were the foundations. But how did we get to the incredible, complex structures we see today? How did space-time build our majestic cosmos? Our entire universe was created in the Big Bang 13.8 billion years ago. Everything came from nothing. But our modern universe is a complex mosaic of matter.
When we marvel through our telescopes at the fantastic structure of our universe and its galaxies, you gotta ask, where did that come from?
Matter in the universe arranges itself on a vast cosmic web. Galaxies and galaxies clusters are strung out on sheets and filaments.
It seems this intricate web is organized by a cosmic architect. Space-time. It shaped everything, from planets to galaxies, atoms to cities.
The universe is made of space-time. Whatever the substance is, time and space bound together, that's expanding and creating the universe we see around us, it's everything. Space-time is what the universe really is.
It's a hard concept to grasp, and even harder to visualize. Scientists observe the universe in different wavelengths of light. This is the sun, in visible light, X-ray, and ultraviolet. Now imagine if we could see it in the space-time spectrum. We would see space-time distorting as objects move through it.
Space-time can warp and push things around. It can expand and pull things apart.
But it's the shape of space-time that dictates how we experience it.
Imagine you're in your car. You go up hills and you go down hills. So the shape of Earth's surface determines how you travel across Earth's surface. In the same way, the geometry of space-time determines how light and matter move through space-time.
The rules are simple. Matter, in fact, any object, tells space-time how to curve. The curvature of space-time tells matter how to move.
Because the shape of space-time tells matter how to move, what we call gravity, this means that gravity and the shape of space-time tells matter how to clump together and form larger and larger structures.
But at the beginning, the space-time landscape was very different from today's. And the very first matter started to change the shape of space-time.
So this space right here has a tiny bit more matter in it than this over here. Wherever there was a little bit of extra mass, that would bend space a little bit more. Well, if you're bending space a little bit more, then more mass would collect there.
In the early universe, the denser regions of matter created deeper curves in space-time.
And as the mass gets bigger, as stuff falls into that well, it gets deeper and deeper and deeper and attracts more stuff. And it's just a runaway process.
Gravity increased, pulling in more and more matter.
Got more dense, got more dense, got more dense, and then before you know it, you've got a star, and you've got a bunch of stars, and you start to make a galaxy. And these stars evolved and began forming large structures. They sort of burned through all their nuclear fuel and exploded, and they made all the heavier elements. And with time, we got down to having things like planets, atmospheres, people, all the things that we care about today.
All of this started out as energy fluctuations in expanding space-time.
These, at first, very tiny fluctuations became these gigantic structures that we actually see today.
And over billions of years, that material began to coalesce into individual galaxies, stars, planets, and you.
Fluctuations in the expansion of space-time laid out the pattern of the universe. The curvature of space-time controlled the evolution of everything we see today.
If space-time didn't have that property of bringing mass together, then all we would be is a thin haze of hydrogen gas. Not a very interesting universe at all.
If space-time didn't curve because of matter inside of it, the universe would be a really weird place. I mean, there'd be no gravity. There'd be nothing to make things stick together.
No force of gravity means no stars, no planets, and no people.
We owe our existence to space-time. But even scientists struggle to understand it.
I wish I knew what space-time is. We know things about space-time, but at the same time, we feel like we know almost nothing about space-time.
Then, in 2015, we caught a break. And for the first time, we heard ripples in space-time, generated by one of the most violent events in the history of the universe. The universe is filled with space-time. We think it's been around from the beginning of everything, quietly pulling the strings of the cosmos. And sometimes we get a glimpse of this elusive puppet master in action. 2016, astronomers witness a strange optical phenomenon, a weird circle of light, like a cosmic halo.
This is actually what you would see in the sky if your eyes were as sensitive as a telescope. They're real. This is not some artifact of how we adjust the images. Something is actually bending space and time itself into a lens.
That something is a red galaxy, which is over 7 billion light years away from Earth. It's bending the light from a blue galaxy, which should be hidden behind it. It's called gravitational lensing.
Gravitational lensing is an amazing phenomenon because it demonstrates explicitly what Einstein told us, that space is curved. And space acts like a lens, just like the lens in my glasses act. And when we look out at the universe, we see all of that. It's remarkable.
Mass from the foreground galaxy creates curves in space-time, which we know as gravity. Light follows those curves and is warped, so it bends around the galaxy.
Massive objects, like clusters of galaxies, can bend the path of light through space-time, a lot like a piece of glass can bend the path of light. So when we look at a distant galaxy, as the light passes through a galaxy cluster, we see multiple images of the same galaxy. We see arcs and circles, as if that galaxy cluster were made of glass. We are seeing the warping of space-time literally played out in front of our very eyes.
Gravitational lensing gives us a way of seeing the effects of space-time on light. But it's only an indirect observation of space-time. Could there be another way of experiencing space-time right here on Earth?
Not everything that happens in space can be seen. Sometimes you have to listen for it as well.
Believe it or not, space is a material much like this iron sheet. And like this iron, space can distort. If I put a very heavy weight on this sheet of metal, its shape is going to change and it's going to distort. Amazingly, space can carry waves. And so can this iron sheet. But to get this sheet waving, you need something really powerful. Something like me and my hammer. Did you see those waves travel through that iron sheet? Well, waves pass through space in exactly the same way. We call these gravitational waves.
Gravitational waves are vibrations from cosmic events transmitted through the material of space-time.
To set off waves in space, you need the biggest, baddest, most powerful events in the universe. Something like the collision of two black holes.
When two black holes collide, the energy released sends shock waves through space-time across the universe. By the time they reach Earth, they're so small, they're immeasurable. Almost. In 2015, scientists at the LIGO Observatory made a groundbreaking observation. They detected ripples in space-time, gravitational waves.
Rumors began flying, but it became clear after a while that this was indeed the first direct detection of gravitational waves seen by man-made instruments on the Earth.
When we discovered gravitational waves, it had been so long that we've been waiting for signals. Not only did most of us not believe it, I went so far as to be so skeptical as to look into all kinds of conspiracy theories for ways it could be fake.
When I saw this data, I still think back on it now, and the emotional impact it has on me. The only thing comparable is when I saw my daughter's face for the first time after she had been born. It was that kind of an emotional impact, just having all of this thing that we had worked for coming to fruition in one moment. It's mind-blowing.
We can actually hear these gravitational waves on Earth.
Part of what makes this so amazing, it's a bit of a coincidence, but it's a really cool coincidence, is that the signals that LIGO actually measures are in the same frequency band as the sounds that the human ear is sensitive to.
We can hear the waves change frequency as the two black holes get closer and collide.
It's a swoop up in frequency that sounds like whoop.
What we were hearing in that whoop were two black holes that are orbiting around one another and then coming together. That was it.
Listening to ripples in space-time has given us a powerful new tool to investigate the universe.
We are now hearing things in gravity for the first time. It's a sense that we have never been able to apply to the universe, and we're beginning to learn what is out there.
The observation of gravitational waves from black holes is one of the most significant findings in astronomy by anyone in the recent 100 years.
It's hard to overstate the importance of gravitational wave astronomy. Much like when Galileo first pointed his telescope at the stars to see something new, we now have an entirely new window into the universe.
Gravitational lensing and gravitational waves offer us an insight into the complex relationship between gravity and space. But what about the other half of the equation? Time.
But it turns out, it's space-time. Gravity not only distorts space, it actually distorts time, too.
We think of time as something that can't be changed. It simply flows ahead at a constant rate. But that's not the universe we find ourselves in.
In some crazy circumstances, my time might even, according to you, stop.
It might even be possible to travel through time and go back to the future. For sci-fi fans, space is the final frontier. For scientists, exploring time is a much bigger challenge.
Originally, we thought of time as the same thing as the sun rising and setting. But now we've come to realize that time is a more fundamental concept than that.
Time isn't just something that passes. Time is an essential part of our universe. It's part of the fabric of space-time. The Big Bang was the beginning of space and time. Since then, space has been expanding and time has been ticking forward. It's been doing this for 13.8 billion years, creating the universe we see today.
Space and time are tied together. They're the same thing.
So when matter influences space-time, it's not just creating deformations in space, it's also affecting the flow of time.
This is where space-time becomes really cool.
Just as gravity bends space, it also distorts the flow of time.
This isn't how we perceive time. This is actually the rate at which time flows.
Very massive objects can warp and twist space-time itself. So not only is space distorted, but time itself can slow down or even stop.
The stronger the gravity, the greater the distortion.
What has the most gravity? A black hole.
Out in space, near a strong gravitational tug from a black hole, clocks can do funny things, and this is where things start getting really interesting.
Around a black hole, space-time warps and twists, slowing time down. Scientists dream of sending a probe there to test their hypothesis.
There's a famous way of thinking about this called the twin paradox, where two twins are born at exactly the same time, right? So they're the same age, but one of them zips very, very close to a black hole, hangs out a while, and then comes back.
If I had an identical twin who stayed back on Earth while I flew near a black hole, when we had our daily video phone calls, he would see me go, "Hi there," and I would see him say, "Oh my goodness, I'm a little bit concerned about you because you're talking so funny." We would literally notice that time is running at a different pace for the other one.
The closer to the black hole, the slower time passes.
If instead of coming back home, I accidentally fell backwards into the black hole, my twin back on Earth would see me slow down even more. I'd go, oh! And completely grind to halt and seem frozen on the event horizon.
Time appears to stand still.
I would just have a sinking feeling that I would never be able to come home again.
But if the twin could escape from the black hole, he would be returning to the future.
Maybe it's only been a few days or weeks experienced by the one that traveled to the black hole, while the other is, gray-haired and has grandkids by now, has lived decades here on Earth.
The black hole warps space-time so much that the ultimate science fiction fantasy becomes reality.
Time travel is a staple of science fiction, and we know that time travel into the past appears to be ruled out in our universe. But time travel into the future is totally acceptable.
Time travel isn't possible just yet, but space-time has a very real effect on our daily lives. It controls how we age.
The key to different rates of flows of time is gravity. If you experience a different gravitational environment, you will have a different flow of time. As I climb up these stairs and I put myself further away from the mass of the Earth, my own clock runs a little bit faster. If you go down closer to the surface, the more your clock slows down. We have sensitive enough clocks that we can measure this different flow of time.
Exaggerate this effect, and we would see the flow of time change in front of us. Those closer to the Earth would look slowed down. Those higher up, the opposite. Which means the wealthy in their penthouses actually would age faster than people on the ground.
This is a mind-blowing concept, but it's reality.
Earth's gravity even controls time high above the planet. 12,500 miles up, there's an array of global positioning satellites, crucial to the navigation systems in our cars and cell phones.
We here on Earth use the global positioning system as a way of getting around. Okay, most people these days would be lost if they have to go more than about 1 kilometer from their house unless they have their GPS app on their phone to tell them where to go.
The GPS receiver in your cell phone bounces signals over 4 satellites to figure out exactly where you are. It's an exercise in precision timing. On board each satellite is an atomic clock. The weaker gravity in orbit means the satellite clocks tick fractionally faster than those on the ground.
If we didn't know to correct for the fact that the clocks on our satellites move at different rates, the GPS system here on Earth would not work.
It would actually lose accuracy at such a rate that the entire global positioning system will become useless in less than an hour. We correct for that every moment of every day.
Space-time has controlled every phase of the universe's evolution since its birth. Now, we're discovering space-time will also dictate how the universe will die. Our universe started with a bang, 13.8 billion years ago. It's been expanding ever since. Will this expansion last forever? Or will our universe come to a violent end?
For almost 100 years, we've now known that the universe is expanding.
Everything in the universe is expanding away from everything else.
We can test this by measuring light from exploding stars. Type 1a supernovas all explode with the same brightness, so scientists can accurately work out their distance from Earth. For decades, astronomers have measured this light being stretched by expanding space-time.
The universe is expanding, and there's matter in it. That matter has gravity, and that is distorting the curvature of space-time.
So it made sense to us that as the universe expanded, all of the matter in the universe would hold on to each other gravitationally.
If there's enough matter in the universe, it can actually pull on itself enough that the expansion gets slower.
But in 1998, astronomers took new measurements and made a sensational discovery.
People had expected it to be slowing down, to decelerate, but instead they found the opposite. The expansion is accelerating.
If expansion was slowing, then these distant lights should seem brighter. Instead, they were dimmer. They were getting farther away, much faster than expected. It could only mean one thing.
That expansion is getting faster. It's accelerating every day.
This discovery turned our understanding of the universe upside down.
For the first 7 billion years of the universe, the rate at which the universe was expanding was going slower and slower. But then something crazy happened. It was as if gravity had become the opposite. Instead of attracting the galaxies, it was almost as if it was pushing them apart.
That's a very surprising result. We're still struggling to understand it.
Was gravity losing its power? Or was there something else pushing space apart?
There's another ingredient in our universe, an ingredient that behaves very oddly.
A mysterious quantity called dark energy.
Like space-time, dark energy is all around us. We can't see it, but it makes up 70% of the stuff in our universe. But what is it exactly?
Dark simply means that we have no idea what it is. We don't know what form it is in. Something is pouring energy into the universe, causing it to accelerate.
We don't know what it is.
No clue whatsoever.
We don't have the slightest explanation. It's the biggest mystery in science today.
Dark energy behaves in mysterious ways.
Ordinary matter is attractive. Dark energy is repulsive. That's why it's causing an acceleration. Ordinary matter feels gravity, it comes together, but this stuff doesn't.
Is dark energy a new force in the universe? Or, like gravity, could it come from space-time itself?
Dark energy may very well be a property of space-time. It may be that space itself has an energy, and it's this energy that's driving it to accelerate in its expansion.
Dark energy is a thing. We don't really know exactly what it is, but it will have a huge effect on the future changes in the universe.
So what will happen if dark energy keeps accelerating the expansion of our space-time universe?
Because of the presence of dark energy, it'll expand faster and faster and faster, which means the universe is going to become a lonelier and lonelier place to be.
All the galaxies are accelerating away from each other. The universe gets dimmer and dimmer and colder.
Everything gets darker and more desolate, and right now that is the leading candidate for what's going to happen in our future.
Eventually, our space-time universe freezes.
The Big Freeze is the ultimate endgame of the universe as we know it. It is an ugly fate. It's a depressing fate, but luckily for us, it's not until an unimaginably long time from now.
Trillions of years from now, the universe could end in a big freeze. But a 2017 study hints at an even more frightening possibility. Dark energy might be getting stronger.
One horrible scenario for the ultimate fate of the universe is if dark energy eventually grows so strong enough that it can overwhelm the gravitational attraction of a galaxy itself.
It's even able to rip black holes apart.
The very fabric that holds everything together could be ripped apart. This idea is called the Big Rip.
First clusters, then galaxies like our own Milky Way will be torn apart. Then our solar system will break up. And in the final half hour of the universe, the Earth will explode. In the final second, atoms will vaporize.
Everything in the universe would individually be torn apart by the expansion of space.
We don't understand dark energy. Is it constant? Is it getting stronger? Is it getting weaker? At this stage, we simply don't know.
The future of our space-time universe hangs in the balance. Will it end in a big rip? A big freeze? Or is the end really just the beginning? Space-time controlled the birth of our universe. It will also dictate its death. Now, we're discovering these two events may be linked. A link that reveals a flaw in our understanding of the Big Bang.
Everything we can now see, all the matter, all the energy in our universe was once contained in a region smaller than the size of an atom.
We call this tiny, infinitely dense point a singularity. Singularities are predicted by the General Theory of Relativity. But the universe is also governed by another set of rules: quantum mechanics.
Quantum mechanics is our description of the subatomic realm, of fundamental particles and fields and forces and how they interact.
Quantum mechanics says that nothing can be infinitely small or dense. So singularities can't exist.
Singularity is a bit where everything kind of goes to hell because the densities become infinite, gravitational forces become infinite, things just sort of break down there and the equations sort of stop making sense.
No singularity would mean no Big Bang as we understand it. So then, how did the universe spark into existence? Scientists now think they have an answer. A solution that works with both general relativity and quantum mechanics. Quantum space-time.
A successful theory of quantum spacetime should answer the question of what really happened in the earliest moments of our universe.
Hopefully, the correct quantum theory of gravity won't have any singularities. It will replace the Big Bang with something else. If we only knew what that something else was, we might have a clue as to how and why the universe began.
In a quantum space-time Big Bang, there was no singularity bursting from nothing. The universe formed from the remnants of another dying universe.
It's possible that before the Big Bang there was still a universe, there was still space and time, but rather than expanding, the universe was contracting.
Perhaps universes don't end in rips or freezes. Perhaps they collapse. An ancient universe expands, but then begins to collapse under its own gravity, crunching space-time down to a speck. But instead of forming a singularity, space-time once again explodes.
As matter gets more dense, then as the matter crunches down, this force will push everything back out.
The universe would bounce and reignite in a new round of expansion, a new Big Bang.
What we perceive as the Big Bang is the aftermath of that bounce.
This suggests that the space-time that dictates our lives today comes from the collapse of an old universe, and we live in an infinite space-time cycle of birth, death, and rebirth. A bouncing space-time universe.
If we live in a bouncing universe, it's very plausible the universe is infinitely old, that it's gone through an infinite series of bounces and there is no absolute beginning.
It could be that we are just one iteration of an infinite number of cycles in the lifetime of some meta-universe.
We barely understand space-time. Perhaps we will never understand it completely. But one thing is clear. Without space-time, we would not be here.
Space-time is something absolutely real. It's really part of the fundamental architecture, the furniture of reality.
To really understand the ultimate fate of our cosmos, it's not enough just look more with our telescopes. We also have to understand the basic nature of space-time.
You really are right now living in a far more complex and beautiful universe than the human mind can comprehend.